Recording. Okay. Okay, I'm sorry. The first part was missed the recording, but yeah, the first part is about the Boolean algebra. That's fairly easy compared to another two different topic. So yeah, let me give the chance to Yuan, and I stop sharing, and Yuan will share his screen and discuss about that structure.
Let's get this. All right, can you see my screen?
Yes.
All right, so we have 4 things we're covering today. We have stacks, queues, binary search trees, and priority queues. So let's take a look at a stack. So a stack, it's a data structure that accepts a last in, first out order. So that means a stack is sort of going to be like a list, but the thing about this list is that it's special and that you can only take things out from the last element. So if we say we can have a stack saying like, let's see. So let's start a stack down here. So say if we add 1 to the stack, then 1 is going to go on top of the stack. If we add a 5, it's going to go here. So the thing with the stack is that you can't, after you add, like say the 1 and 5, you can no longer insert anything other than to the last element. So you can't insert it here or you can't insert it here. These are permanently locked unless you say remove the 5. Let's see. And if you remove the 5, which means because you can remove the last item, then you can access the first item and then you can insert something else. But once you have, say, like 1, 2, 5, 3, you can't insert anything at the 1 spot, the 2 spot, the 5 spot, but you can insert at the 3 spot because it's the last element. So you can see, I just talked about it. We have 2 operations here, push and pop. Push, I was just talking about it. You can push inserts an element to last, to like the last place in the stack. And then pop, it's going to pop the last element in the stack. So if we say pop on this stack right now, we have a 3, so it's going to pop the 3 out. And if we do pop again, we can pop out the 2. So with a pop, we also cannot pop, say, the 1 out right now because the 3 is the last element. So therefore, you can't pop out the 1. So that's basically what a stack is. Let's erase that.
Wait, so push is wait, so I don't understand. Push is adding something to the beginning of a stack, and then pop is removing something from the end, or is it not removing?
So push and pop, they both are at the end. So if we're pushing something, we can only push to the end. If we're popping something, we can only pop from the end.
Wait, so I still don't get it.
I have one question.
Yeah.
That's how we part the middle, the center to the 5. How we change the 5?
So the thing with the stack is that we can't do that. That's the sort of like the purpose of the stack. Because like that's sort of like the purpose of what the stack structure is that you're not supposed to be able to access what's not on the top of the stack, or you could say the end of the stack.
Okay, got it. Thank you.
So like the push and pop, returning to the original question here, the push and the pop, they can only like operate on the last element. So they can only operate in this case on the 5 because it's the last element. We can't do anything on the 1, 5, 3, or 4. So does that answer your question about that?
A little bit. So push is like, so is push like, say you have 1, 5, 3, 4, 5 as a stack, and then if you run the push command, would it just put the 1 behind? So like 5, 3, 4, 5, 1, or?
Yeah, so push it behind.
Also that would be like the same as like in bit string flicking, like the like circle like command.
Sure.
Okay, and pop is
it's taking out from the last element. So in this case, we have 1, that's the last element of the stack. If we do pop, it's going to take out the 1.
The pop is basically just deleting the last element.
Yeah.
Okay.
And like the thing about the stack is that like we can't do anything else other than adding to the last element or deleting from the last element. We cannot like insert into the middle. So David tells me here that I should draw it maybe sort of like this. We can understand it better. So say we have like this is a stack. And then the thing about the stack is that we add on top of the stack. And then we can only remove from the top of the stack. So there you go.
You can't. So it's like a list, but like you can't.
Yeah, it's a very limited list.
Okay.
So that's going to be what sort of a stack is. All right, so here we're going to have a stack operations. So well, we can sort of just like sort of simulate this to see how it goes. So push A. So currently we're going to have, say, an empty stack here. So let's start a stack here at the bottom. So if we're pushing A, we're going to add A onto the stack, like so. Push M, then add M on top of that. Push E, put that on top. And then we get the first pop operation, which means we're going to remove the top object. So that's going to be E. So the E is gone. And then we push an R on top. And then we remove the R since it says pop. We're up to here. Then remove the R. We push the I here. And then we get 3 consecutive pops in a row. So it means we're going to pop the element starting from the top. So we have I, M, and A. So now it's empty. Why is it asking to do another pop? That's odd. And then, well, whatever. So then we push a C, and an A, and then an N. All right. So let's continue. So a queue is sort of like a stack in that it's a limited list, but it doesn't function the same way as a stack. So a queue, you can think of it, say, like waiting in a lunch line. So if you say, I'll draw the lunch person in blue here. And then, so we're going to have, say, like one person comes up and then they get lunch, right? And another person comes up, they're waiting in line. And then, of course, the lunch lady is going to be serving the person at the front first. So that means as we get more people, let's draw a few more here. That means that the person in the front is going to always get served first. And then once that person is served, next person, next person, next person, next person. So that's how a queue functions. So say if we have we add 1 to the queue, what if we add 5, 3? Then if we do pop from the queue, always the element at the beginning is going to get removed. So in this case, since 1 is at the beginning, we're going to take it out. And then next we're going to get the 5. Next we're going to get the 3 out. So that's what they mean by the first in, first out order. Whoever comes in is first out. So again, we have limited operations here. We can only push and pop from the queue. All right, so here's some queue operations. Let's draw a queue here. So we add A onto the queue. We add M onto the queue, and we add E on the queue. These are these. Then we pop the first element. In this case, the first element is A because we added A first. So we're going to remove the A. And we want to push an R, so we're going to add R at the end here. And then it wants us to pop, so it's going to pop. We're going to pop the M, since that was the first element now. And then we're going to get up to push I, so we add another I into it. Then we have 4 pops. I don't know why it's asking for another pop. You shouldn't be able to do that, but there we go. So now the queue is empty. And then we push a C, push an A, and then we push an N. And then if we were to pop again, we would take out the C because the C was added in first.
So if we're going from left to right, push would add a number to the left, which is like
Yeah, and then pop would remove number from the right.
So So say we had a queue that had 1, 2, 3, 4 in it. So if I pushed another 1 in, would it become 1, 1, 2, 3, 4?
Well, so push, it adds on to the end. So let's see here. So if we had, say, 1, 2, 3, 4, assuming that 1 is the beginning, we had another 1 to go at the end. But if we were to pop from it, the popping would take place at the start.
Oh, so it's like circulating, kind of.
Yeah, sort of. You could call it that way. Yeah. All right. All right. So binary search trees. So the purpose that these serve is that these are, we can use these to say like more efficiently search through a data structure. So let's look at something first. So consider this. Say we have a list here. Say we have 1, 2, 5, 9, 3, 4, 6, 7, 10. So if we were to ask ourselves, is 9 in this list? The computer would have to search is through every single element in this list independently. So it would have to go through all of these items to figure out if there was such an element. So a binary search tree alleviates that problem by making the data sorted. So like that means that it's going to be way faster to find things, since you're going to be like you're going to know like where the item is expected to be. So it's just like if we had instead say we had like a 1, 3, 5, 9, 11. Say consider this list now. This list is sorted. That means it's going to be much faster to find the item. So the way that binary search works is that we ask ourselves, is 13 in this list? So the way that it works is that we pick the middle item in this list, but in this case, there's no middle item because there's 6 items. We're going to pick the 9 here. And say we're searching for 13. So that means we pick the middle item, we see that's a 9. So that means we know that the 13 must, since 13 is greater than 9, we know that the 13 must be on this side of the list only. So that means that just eliminates this side of the list entirely since it's sorted. That means there's no way the 13 could be to the left of the 9. And then we repeat it again with the middle item in this box. In this case, it's now 11. We ask ourselves, is 13 greater than 11? It is. So that means the 13, if it were in the list, it must be to the right of the 11. So then we look to the right and we see a 13. So that means 13 is the list. So we can see how binary search works there, and that it basically speeds up our searching algorithms by sorting the list. So a tree is basically sort of the same thing. So say if we were searching for if there was a 31 in this tree. So we would start at the 27, and then we would ask ourselves, is 31 greater than 27? Well, since 31 is greater than 27, we're going to go to the right node. So now that means that we're in if 31 were to be in this tree, 31 must be in this section. It can't be in these sections right there. So that means we don't even have to consider those. When we look at the 35, is 31 greater than 35? No. So that means we're going to go to the left node now, which is this one. And we see that this left node is 31, so that means 31 is in this tree. Let's see here. So binary search can not only operate on numbers, like the example I just showed you, it can also operate on letters. In this case, if we write the word American here, A is going to come first, and then Z is going to come last. So that's the way we can do that there. Let's see here. All right. So if you can see here, a binary search tree just knows that the key at every node is always greater than or equal to the key of its left child, and always less than the key of its right child. So here is the searching algorithm that can be used to search for nodes in a binary tree. I just demonstrated that to you in the previous tree. So let's see here. So when P is not equal to nil, so if it's less than P's key, we're going to go to the left child. Otherwise, it's going to the right child. And then once it does this, it's going to loop back around again until it finds it, or it does not find it. Then otherwise it's false. All right. So here is a priority queue. So this is the final data structure we're going to talk about. Actually, let's pause here. Do you have any questions about binary trees?
So could you give like an example of a question regarding binary trees? Because like I understand the concept, but how would that be used in like a question?
Actually not sure. I could check the questions for you. I'm not actually sure what type of questions there could be. There could possibly be like asking like maybe a question about like how binary trees work, but I'm not sure what questions, but as long as you understand the concept, you should be fine if they do ask you, say, a binary tree question. All right. Is there any other questions, or can we go on? All right. So let's talk about priority queues. So priority queues are like a binary search tree, except one cannot delete an arbitrary item, nor can one make an arbitrary query. So the thing here is just, like I said, the stack and the queue were limited lists. This is a limited binary search tree. So the only operations we can do is finding out, querying, or deleting the smallest element of the list. All right, so the way this works is that, say, well, we're not going to draw this out of a tree structure. So let's say this 7, 4, 6, 2. So in this priority queue, we're going to call it here, if we were to say pop, we would pop out the smallest element. In this case, that is going to be a 1. So the 1 is removed. Then if we were to pop again, we would see the 2. The 2 is removed. Then the 3, 6. And then if we're adding, we can just mostly add this on top of anywhere. I'm not drawing this in a binary tree fashion, so you can't really see the tree. But if we here, we can add it. But then we can only pop the smallest element. So down here it says that the only way to implement this, the standard way, I mean, is to use a binary tree. And it just maintains the property that every node is less than or equal to both of its 2 children. All right. So here, so here is sort of a priority queue for you. So here, this just shows adding, but if we were to say like remove from this priority queue, we would remove the 1, then the 3, 5, 9, 12, and 15. So that is sort of how a priority queue works. So there we go. Do you have any questions on that? All right, that seems to be it.
Great job. Thank you. Yeah, if you have any question, you're welcome to post a question here or post a question at the Google Classroom. Let me share my screen. Then we are running pretty smooth. So I assume most of you got the basic idea. Okay, so that's past the second topic. And we are talking about the third topic. Again, this third topic is only for junior division. And we have pretty much repeats the same topic again and again. It's something they called what does this program do? So basically, this is really something about how to understand the program. Instead of write your own program, sometimes you need to understand the program written by other guys, so you will not get confused. If you are really advanced enough, sometimes you can do the code review with other people. So yeah, it's really the engineering stuff, but mostly here we use a pseudocode. So it's not really bound to specific language. For example, if you're learning Python, but you don't really know the Java, don't worry about that. It's really about the pseudocode. The pseudocode means you are not really writing the real code. Instead, you are writing something which just try to simulate the whole code flow. Okay, so we use the operators first. This is not, and this, you probably not really able to use this, but you can use this. It's the explode, and this is for the real division. This for modulus, plus, minus, larger than, smaller than. This is very straightforward. And you have the function. Of course, the function is represented like the function name with the parentheses, and this is parameter. And of course, you have the variables. You have the sequence, but the sequence here is written like input and variable, and the variable with the expression, assignment, and then the output. Okay. You have something called the decision statement. So you have if, then, else if, or while loop, while something, and while. I don't really here to give you too much details, but you just need to know that all of these are pseudocode. So it has nothing directly to do with Python or Java or any other advanced language. And here you can use a for loop. So it's pretty straightforward. You have the start and end, you have the step increment or decrement. So either way, and then you have the statement in between of the for and the next. And you can define the array. So one-dimensional array is like this, or two-dimensional array is like this. So you can pretty much just like draw a table, and you can put the element in that array table. Of course, string is something used most often, but if you see here, they are slightly interesting is that they try to get the substring from this string. So I don't really come here to teach you step by step. Instead, we are really trying to go over the big picture. So if you have interesting to know more about that, just try to understand that. We will post this and you can really study that. This means from the very beginning up to the third, the first three characters, and then the last four. So that means this to the end, and this is last means 4 to the end. And then this is start at location 2 and end at location 6. This really means the first one. So that means the first element. Okay, here. So here is a quick example. So for example, if they have a question, ask you, if you see this program, of course, this is pseudocode. And what's the value of B print out if the input value of 50 and 10? Of course, you can pretty much put that on the paper, or you can use a program. Since you only have 30 minutes, so sometimes put on the paper is even better than put in the program. I will give you 2 different methods, show you both way. So if you put on the paper, it's pretty straightforward. So you have H here is 50, and then R is 10, right? Okay, so you have H and R, so you can put on the paper. Let me show you the virtual board. Yeah, I'm sorry, I have one account, but somehow I didn't log in. Okay, so let me put on this side slightly small, maybe make it bigger so you can see it clearly. Okay. Okay, so I have a new board, create a shared board. Okay. I hate that. But anyway. Okay, don't worry too much about that. I use another one. I know that one is not really the perfect one, but it can work. Okay, so now you have Jesus. Why? Okay, so now you have H and R. You can put the H here and R here. And then the B is really the result, right? Okay, but you have the intermediate result. Okay, so the H is 50 here. And R is 10. So now you go to here and you know the input is H and R, and then B is 0. So the initial is 0 here. And if H larger than 48, so now it's 50, it's larger than 48, right? So now we will go to this statement. B equals to B plus H minus 48 times 2 times R. Okay, so this is a little bit confused, but if you put on the paper, it's nothing really hard. That means this will be B, that's 0, plus H minus 48. So that's 50 minus 48. And times 2 times R times 10, right? So now you get this will equal to what? So you can make the quick calculation. So that's 50 minus 48, that's 2. 2 times 2 is 4. 4 times 10, that's 40. 40 plus 0, so that's 40, right? So now this is 40. So after this step, B is 40. And H is still 48. So you get out. So we get here. We know the H become 48. R, we don't really change, so it's still 10. And B becomes 40. Now you have the H larger than 40. So now H is 48, still larger than 40. So you will calculate this. So that's B. Now B is 40, right? So you will see the B is 40 plus H minus 40. So that's H is 48. So that's 48 minus 40 and times 3 by 2 times R. The R is 10. Right? So if you make quick calculation, so here is 8. 8 times 1.53 divided by 2 is 1.5. So 8, you can say 8 times 1.5 times 10. So that's really 8 times 15, right? So that's 90. 90 plus this 40. Do I make some miscalculation? Wait a minute. B plus, okay, B is 40. 40 plus 48 minus, so this 8 times this 1.5, 8 times 1.5 times 10. So that's 12. Okay, so that's 8 times 1.5 is 12. 12 times 10. So that's 120. 120 plus 40. So that's 160, right? So now you got B is 160. And then H become 40 again. And R not change, so it's still 10. So that's really the second part has been calculated. Now the final step is B equals to B plus plus this Okay, so now B is 160 plus H is 40 times R is 10. So that's pretty straightforward. We know how much that is, right? So this is 400 plus 160, so that's 560. So that's B. That's really the final. Yeah, if you want, you can put the H here and R here, but you only need to give them the answer. What's a B? B is 560. So that's pretty straightforward. That's something I want to show you. Of course, this is a very easy example, but if in case you want to go through that, I suggest you go through that on the paper. Of course, if you have time, let me see. Jesus, why cannot you access that? Cannot be reached. Oh, sorry. Yeah. I don't really get the full copy. Okay. So if you have time, you can convert that into program. So that's really not very hard. For example, you can ask them to enter H and enter R, and then you can code line by line. So you have the B equal to 0, H larger than 48, then you can do this, H larger than 40, you can put two statements here. So now let's run. Okay, just assume now the H is 50 and R is 10. So now you get 560. Okay, so that's two different methods and both will come out to the same result. You can code it. For example, you are familiar with Python or Java or even JavaScript, you can do it. Or if you want to put just on the paper, you can do something like this. I think if you don't have enough time, put on the paper probably is slightly easier, but sometimes put in the coding will make it precisely running, because here you can make mistake by calculation. But if you put the code correctly, you do not really make the mistake, especially if some of this logic is kind of trivial. Okay, so that's pretty much what we want to present today. And is anybody have any question? Yeah, I think this example is pretty straightforward. Sometimes you have the question, it's a little bit more challenge, just take your time. I know the coding part 72 hours. A lot of times you don't really have to spend all of the 72 hours, probably 4 hours, 6 hours, or 8 hours at the most. Yeah, but in case you don't really understand certain concept, go to here and just check out the video and articles. And we try to post the best one, not really necessary to be a lot. So try to go through one by one and make sure, for example, for the Boolean algebra, and you can go to one of the videos and say, oh, what's a Boolean algebra? So now I'm going to show you how I use Grammarly. Okay, so yeah, they'll really give you some simple example, and they'll really discuss about how to make the solution out of the question. So yeah, I strongly suggest you to go through this video. Each video is about 15 to 20 minutes at most. So it will take a little bit time, but believe me, it's much better than just try to put on the paper without really looking for some of this explanation. Okay, again, any question, please put on the Google Classroom, and we have the homework assignment. For junior division, we will have the second assignment for the second topic. So that's about that structure. For the elementary division, we will have extra Boolean algebra question. Okay, so if you don't have any more question, we will start today's meeting. And again, I hope you can continue practice. The time for the third round, let me see, the time for the third round should be at the first week of April. So you have another 2.5 weeks to prepare for that. Just spend your time wisely, especially over the weekend. Okay. Any question?
Can you share the slide on the Google Classroom?
Excuse me, which one?
This slide you present right now.
Oh, you mean this slide? I will post it as a PDF on the Google Classroom. Yes, I will post over here.
Okay, thank you.
Yes. Okay. Yeah. If no more question, we will end today's group meeting, and I hope over the weekend you will spend a little bit of time to practice. If you have any question, please post on the Google Classroom. We will try to answer the question. Oh, I'm sorry. Post the Zoom link. Yeah, I don't even realize that until this moment. But I see Eric, right? So Eric is here. Yeah, is Eric here? Yeah, Eric is here. Okay, thank you. And yeah, you have a great weekend and see you probably next month. Yeah, okay, bye.
Bye. See you later.
See you.
Bye.
Bye.